So thank you very much for being here and for organizers to inviting me here. So, well, a couple of words about how I ended up here. So, first of all, I work in this building and I do some teaching and some research. And, well, the main direction of my research is machine learning and deep learning. And I work with both images and some problems related to languages. So, well, I know that the hype nowadays is more about the agents, not the fine-tuning LLMs and the stuff, but we had specific data sets for which we realized that, first of all, well, some existing models are not operating properly, and we need to have some adjustments. And, well, we have some other constraints as well. So another one can be that, well, we work with some companies which are not interested to have their data uploaded into different spaces, or they don't want to share it with other companies. So we have some restrictions. We're interested to do something in-house, or even if we're planning to buy something as a GPU or some online compute, we're interested to understand how much we will need at all. So again, given all this hype, I tried to understand whether people are still doing this fine-tuning. And here, I tried to extract the number of papers that appear in archive.org, which use several fine-tuning approaches. And, well, this represents that data for recent couple of years, and you can see that some people really use it. And, for example, for the simplest approach, which probably all of you know, is supervised fine-tuning, well, there were more than 600 papers appearing there. So I guess there would be many more attempts in GitHub and so on. So again, not being a person who does this fine-tuning regularly, I tried to answer to several questions, first of all, for myself and for teams I work in. First of all, which kind of LLMs I can fine-tune? Does it make sense at all? And, well, what should be the budget if I want to do something in particular? How much compute do I need? Can I do it in local GPUs that we have here, or I need to buy something? And I tried to do some basic estimation. So, well, I'll try to briefly speak about some fine-tuning approaches on a high level, and then I'll try to show some experiments that I did using my own machine, and some approach I adopted for scaling up and understanding how much compute will I need. So first approach, and the one people use quite often, is supervised fine-tuning. So the formula you see here can look a bit ugly, but it's basic cross-entropy loss. So you basically tell the following here. Well, my model is able to do something, and, well, in general, so if we speak about the machine learning and deep learning, the core thing is the loss, so you try to minimize loss. So you want to have a model which understands or is able to distinguish between many possible answers the correct one. So if, let's say, there are 10 possible answers, and your model guesses that the correct answer has the probability of 0.99, it's a good model. It means that we will have a small loss for this observation, and hopefully we have similar small loss for others. So on average, we're doing a good job. So we're interested in minimizing this loss. So in this supervised fine-tuning, you just say, okay, I have prompts or questions, and I have correct answers to them, and I try to push it into the model and try to make sure that some weights or all of the weights are adjusted in the way to make decision on these new examples better. In other words, minimize the loss. So another approach is DPO, and here there is one main difference. So now you don't give one correct answer, but you say, there are two answers. One is a correct one, another one is a wrong one. And so you have kind of let me put it in this way. You have two models. One is the reference model you have. Let's say you took a 7 billion model. In this case, we're going to use Quen. So this is your reference model. This is what your model knows. And you want to train something on top of that. And you have some policy model. So you try to adjust some additional parameters onto it. And in this case, you know that your base model knows something regarding this question. So you have a basic question. We have an example here. So I tried to put the same example on several approaches. Probably I will shift for a moment back to just read it for you. So Natalia sold 48 clips in April, then half as many in May. How many altogether? So, well, it's easy for us. 48 plus half of it, so it's 72. It's going to be a correct answer. So in this case, we can generate some wrong answer, which would be 96 in our case. And, well, at some point, if you don't touch your model, it knows answer to it. So it either does it correctly or in a wrong way. And by training this, you want it to understand the true answer better, or predict true answer better, and avoid predicting the wrong answer. So here you try to kind of teach what is good and what is bad. Well, another approach stands for, well, the name is ORPO. In this case, instead of comparing this behavior with the reference model, you try to just define the odds ratio. So if this model does this correctly, or probability of answering correctly is high, we will calculate the odds ratio. So we will have probability of true answer and probability of wrong answer divided onto each other. And if this ratio increases, it's good. Okay, so again, you have two answers, good and bad one, and you try to differentiate between them, and you try to teach the model to understand correct things better. So the advantage of this approach is that here you don't use a reference model, so each time it is not uploaded to your GPU to understand what's going on. Instead, you use this odds ratio. At the same time, it is accompanied with supervised fine-tuning, which was the first basic approach. And we have GRPO, something which is used and introduced by DeepSeek. So it's more fancier, and it's quite related to PPO approaches, which is reinforcement learning. So I'll try to just again speak about the idea here. So in this case, you say, well, instead of 2, let's have several of them. Let's say 10 answers. And it would be good idea to be able in the beginning to differentiate between them. So the simplest form is, in this scenario, you have correct answer, which is 72, and 9 wrong answers. But, well, in more realistic example where you have a text, you try to have several answers and understand which ones, so the relative correctness. And you try to teach the model the same thing. So you try to well, give all these examples in the training period, and if models start to differentiate between them, understand their relative ranking, it's good. It means that loss will increase and the results are going to be better. So there are many other approaches, but these are the ones which are pop up when you start to digging into this direction. So, well, besides these approaches, there is another decision to make, which is related to to what extent you want to fine-tune the model. The first simple thing, I mean simple in terms of idea, not the implementation, to do full fine-tuning. So try to adjust all the parameters, which most probably will be a huge task, and mostly people nowadays try to avoid it. Well, some claim that it's useless. On the other side, it is quite costly. Another two approaches people adopt nowadays are LoRa and QLoRa. This is the approach I was speaking about. So you try to kind of train additional layer based on your model or around your model, which tries to understand some new logic or tries to capture some new information you have in your data set. QLoRa basically does the same thing, but it has a huge advantage in terms of compute it uses, because a regular LoRa uses 16-bit system for reservation of the data and the information, in particular here, the parameters which we are interested to adjust. On the other hand, QLoRa does this does it in 4, and it's relatively cheap to run it, especially because you're going to, from model to model, you're going to upload all or part of these parameters to GPU, and it's a good idea to have smaller weights. Of course, this is not something which comes without a cost. If you want to preserve the reference model in a cheaper environment, it loses some kind of information or sharpness, let's say. So one more slide on this, and probably I will switch to some basic results I have. So as you can see, for 2 of the models, it is mentioned that we need reference. So for example, for DPO, you need to have this reference model, which every time for every batch or for every example tries to understand what's going on and whether you're doing good compared with this reference model. On the other hand, for ORPO, you don't need it, and instead what you do is just odds ratio and the regular SFT, for which you again don't need it. So again, if you're planning to fine-tune a model, you have a huge choice, and there are many models you all heard about. Here we do a basic experiment based on these Qwen models. We pick 3 of them, and we are going to work with this GSM8K dataset. You have seen one example from it. So it's basically a school math. You have something like 8K training data and a bit more than 1K test data. And we're going to use one machine with RTX 3090, sorry. And okay, so probably these are a bit small, but I'll try to elaborate on them. Okay, so we have 3 models, as I said. So the smallest one has 0.5 billion parameters. The next one has 1.5 billion parameters. The third one has 7 billion parameters. So beyond this, it was not possible to generate some reasonable results on RTX 3090. And well, what I did here, I tried to run these approaches on these three different models and see what's going on. So on these green highlighted ones, you see for each row which one generates a better result. Well, again, this is just a toy data set, and they may not be very informative, but again, even though having some small data set, well, you can affect the results and accuracy. So the first column is just reference on the base model. The rest ones are the references after applying one of the approaches mentioned earlier. So, well, some time that is consumed during this process is this pairs generation for DPO or ORPO. And well, I didn't have at the moment accounted for this time spending. So this is just another visualization of one row. So for 1.5 billion parameter model, we have that DPO outperforms the rest. But again, so if you check the literature, there are results where, if I'm not mistaken, there is a 1 billion parameter model which is able to go beyond 80% on this toy data set. So here I have some information regarding how many pairs were generated for this experiment, and probably, well, what I'm trying to do at the end, and I have some information which is useful for this, is for each observation or for each pair or for each prompt, how much time was consumed to generate, fine-tune the model. And as one may expect, well, the cheapest one is SFT. So this DPO and GRPO, in my case, on my machine, generated more or less the same results in terms of speed, and GRPO is something huge related to them. And what I did and how I'm planning to use all this stuff is to understand what would happen if I scale this. In particular, so I have some problems to solve, and I'm interested to devote some budget to it. And well, in this case, I just try to scale for 10K training data set and to see how it will work and how much time, how much GPU time I need for this. And as expected for GRPO, it's the highest. So this is the same for 7 billion model, though I excluded GRPO here because, well, it's not that useful in this case in general. But for example, again, this is something that I can mark for me. So I have, well, I need to have some 3 hours of GPU to just train 7 billion model, this model highlighted here for one epoch for 10,000 examples. Well, so I'm running out of time, so 2 slides briefly. So I tried to check, well, of course, whether some information which is known or publicly available is binding for my case or not. So here I have the GPU memory requirement for different models, and the ones which are highlighted or in bold are the ones which I generated, well, when I was running these experiments, I've seen in my machine, so maximum numbers. And well, for example, if I use 7 billion model and I do LoRa, the maximum GPU memory use that I've seen was 22.2 gigabytes. And well, if you know, the capacity of it is 24, so it was quite close, but it was able to run. So, okay, one more slide and I'm done. So the main purpose of me doing this, well, probably two reasons of doing this. So first of all, I'm interested to estimate how much I will spend if I do some real experiments. And here I have some estimates. So for example, for the same 3090, you can find it online for 50 cents per hour. And well, I try to understand, okay, how much money do I need to, for example, fine-tune a 1.5 billion model? If I choose, let's say, 2-3 models, I train each of them through 2 or 3 times from 2 to 4 epochs and this kind of stuff. So based on my estimates, I try to understand how much money do I need. Of course, numbers here are small because I chose small model and number of training data is small. So advantage of having something like this done in-house is that you know that you already have some codes which are running properly, and you can easily scale it up, and you can try to just pick the models you're interested in and estimate some realistic budgets for it. So this is how I'm going to use it. Okay, I think that's it from my side. Thank you very much.
So, is in your setup everything is fixed, like training and testing data, and only variation is done regarding the objectives?
Well, since again this was a small-scale experiment, I tried to minimize the difference to make it comparable. For example, it's difficult to compare in terms of accuracy SFT with, let's say, DPO, because for SFT I use all samples. For DPO, we just generate some pairs, which, well, to have some smaller scale and to have enough compute and time to get some reasonable results. But there can be some other differences as well. In this case, what I can claim regarding, let's say, these basic approaches, be it DPO or GRPO, if we preserve like a rank or the batch size and increase just the number of samples, I'm going to use more or less the similar compute, and I can use the same RTX, and just the time is what is going to be challenging for me, so I can just simply linearly scale it up and hopefully get some reasonable estimate.
So, sorry, can I follow up?
Sorry?
Could I follow up?
If there are no other questions, by all means. There are other questions.
Okay,
Keep your question and then get back.
Thank you for the talk. I just wanted to have your opinion in something. So, for example, the Quent 1.5 billion parameters. I'm trying to fine tune it for the SQL query creation, for example. I have whole company queries and I want to fine tune it with this model. In your opinion, like how many hours will it take if I'm using 4090 for RTX 4090, for example? And because here you are using 3090, right? If I'm not mistaken. Okay, let's say 3090. How much time will it take? And if the data is the company data, like like maybe 20 years old company, for example.
So this is exactly what I try to do here for myself. But to be able to answer to your question, so we need to try to understand, well, this dimension is simplified a bit, like how many observations you have. It depends on how huge are they and the stuff. The next thing is just to do a small experiment, which would cost you like several dollars to go with this SFT, GRPO and DPO for small scale, and try to scale it up to have some reasonable estimate.
The problem is not the budget. It is we already have the GPU, so I'm just want to know. The important thing is the time. It's not the budget.
Again, we need to try to have a basic setup to see how it consumes. I mean, the easiest way, you can ask like any LLM to estimate it for you. But in my case, what I get as a first guess and what I get as an answer as a basic estimates, as a basic experiment were quite different. But again, you need to do some basic setup to see how it goes, then scale it up. So this is exactly what I suggest.
Okay. Thank you.
Thank you for the talk. Is scaling always linear? The scalability, is it always linear, or there's some logarithmic growth, or how fast? If you scale, your graphs are linear, but is growth always linear as you increase your data?
So first of all, for GRPO, it's completely different story, and you're going to have problems. So it's not linear, and I didn't even try to scale it up. Well, if you don't have any other problems with, let's say, the memory issues and the stuff, if you preserve the same rank, the same batch size for a given GPU, I don't see any reasons for it to scale, to have non-linear increase. So you can put a regular checkpoints, even if you have some other issues, you can go back with it. It's not going to be perfectly linear. I would prefer to have myself done like several experiments for different data sizes to make sure that I have a better estimate rather than just a line thrown there. Okay, thank you very much.
So maybe one more question because we need to prepare for the next.
Yes, I'll about index stage with the speaker
Okay,
to
good.
keep line. Thank you so much.
Okay, thank you very much.